Hi, my name is Keith Scott. I'm going to give an update on where CCSDS is in standardization of the bundle protocol suite. So where I'm coming from on this, I'm now retired. I worked in communications in austere environments from 1997 to about 2023, working on DTN since 1998. And sort of throughout that time, I supported the NASA standards program and CCSDS, where I chaired the Space Internetworking Systems Delay Tolerant Networking Working Group, which is the working group within CCSDS that's devoted to standardizing delay tolerant networking protocols and the bundle protocol. And I also served as area director for the Space Internetworking Systems area within CCSDS. And I'll talk a little bit about sort of what that covers. But today's talk is mainly about the work of the DTN working group within the Space Internetworking Services area. And I've also supported the IRTF back when the IRTF had some working groups in interplanetary networking and then delay tolerant networking, and also the IETF working group in delay tolerant networking. CCSDS, or the Consultative Committee for Space Data Systems, was formed in 1982 with really two goals in mind. One was standardization of communications mechanisms with spacecraft in order to allow the different agencies to help each other out and cross-support each other. That has, in fact, allowed saving a couple of missions where a spacecraft managed to get in trouble, and it took resources from another agency to be able to communicate with that spacecraft and get it back into a safe mode and then back into operation. The second driver is a cost driver. The space for equipment for communication with deep space spacecraft is still quite small, and so the agencies were looking to build essentially a single larger market, so that commercial companies that wanted to build hardware to support them could build one set of hardware that would serve all of the agencies instead of having to build separate hardware agency by agency. This slide looks at a little bit of just sort of snapshots in the history of CCSDS, going from sort of the change from commutated telemetry to packet telemetry through this SLE and cross support transfer services are the mechanisms by which agencies intercommunicate in order to exchange the information needed to cross support each other. So when things go wrong with, as I was saying, when things go wrong with a spacecraft from one agency, another agency can communicate the mission needs of that spacecraft. What are the frequencies, modulation, coding that it's using, how to communicate with it, so that communication can happen via the assets of a second agency. And then finally on the right, we're looking at the move from sort of point-to-point communication, which is the way that most of these missions have been carried out so far, to actual networked communication, where you can have a number of nodes on one shared network, and then it becomes easier to add and extend that network because all you need to do is be able to communicate using the networking protocol, and then you can communicate with any other node on the network. This chart shows the CCSDS agency participation. So there are 11 member agencies and 33 observer agencies, and then 141 commercial associates. This goes back to what I was talking about building sort of a single marketplace for space hardware and software for operations. CCSDS also functions as an ISO subcommittee, so the CCSDS standards are typically then turned into ISO standards as well. Even though CCSDS has broad support from the space agencies, that's still a relatively small organization. So they're looking to form alliances wherever they can, and this shows some of the outside organizations with which CCSDS communicates. So there's work going on with the object management group. There's work in coordinating with the European Consortium for Space Standards. The things that we're probably more interested in here are work with the Internet Engineering Task Force and the Internet Research Task Force, which are looking to standardize bundle protocol and delay tolerant networking protocols. There's also work going on with the American Institute of Aeronautics and Astronautics, There's work across, again, the whole spectrum of things from modulation and coding, position navigation and timing, networking, data representations, things like that. Organizationally, CCSDS is divided into 6 technical areas shown here. So these 5 colored pillars, plus the systems engineering bit up at the upper right, which is sort of cross-cutting across multiple of the other technical areas. And each one of the technical areas has some number of working groups at any time going on. So the work that I'm going to be talking about mostly today is work that's going on inside the Space Internetworking Services area. And then within that, mostly the delay-tolerant networking working group. There's other work going on there in motion imagery and applications and voice. And some of that work is interested in how to do, for instance, voice and video over bundle protocol, which might not seem like an intuitive application at first. But one of the things that they're interested in that for is using the reliability mechanisms of the bundle protocol sort of in conjunction with real-time delivery. So using, by sort of marrying up real-time delivery of some data with eventually reliable delivery of all of the data, you could do things like if you're if you're on Earth monitoring something that an astronaut is doing, if there's a communications dropout, you might lose video for some period of time. But if the communications comes back and then the holes in that video are filled, then you could go back later and sort of DVR your way back into the area that was lost and find out what happened when the communications were out. This slide lists most of the DTN related work that's going on in the DTN working group in CCSDS. I'm not going to go through all of this. I've got a couple of slides coming up where I talk about individual pieces of this, but I wanted to use this one to talk about 2 things. One is all these colors, and then the second, which is probably more important, is this concept of a protocol profile, a thing that CCSDS does, particularly when adopting protocols from other organizations. So the colors here, the key is down there in the lower left. CCSDS puts out various documents. The documents are color coded by whether they're informational recommended specifications or single agency specifications. You can think of the single agency specifications sort of like one agency has decided to do something a particular way, and they're looking to standardize that within their agency, and they think it's a good enough idea that other agencies might want to pick it up and use it as well. And we're using that as the driver really towards getting some consensus on recommended specifications. So you can see even that things like the CCSDS profile of Bundle Protocol version 7 is right now being worked as a single agency specification. And we're doing that mainly because it's faster. The recommended specifications, they require review by all of the space agencies, and those reviews take time because the space agencies go out and review that with all of their contractors, and like within NASA, they review it within all of the centers. And in particular, for some things like Bundle Protocol version 7, we're now under an extreme time pressure to get something out that agencies can use in procurement specifications for things like the NASA LunaNet project and the ESA Moonlight project. So the single agency specifications are sort of the forerunners, if you will, in many cases of full recommended specifications. The little chevrons there, the bullets are sort of divided into two types. There's regular bullets. The little chevrons are the things that the DTN working group within CCSDS has identified as the things that are sort of their top priorities for the moment. And the second part of this is there are several places on here where you'll see like profile of and then a specification coming from generally the IETF here. The rationale there is that we're working with the IETF and their development of the various protocols in the DTN stack. But there are some things that are more specific to space communication that might require constraining the protocol that comes out of the IETF in some degree. The objective there is always to maintain interoperability with the IETF spec, but to maybe modify or implement pieces of it in ways that are more amenable to space communications. And so as an example, in the Licklider transmission protocol, RFC 5326, there are some places in there where in order to identify sessions, the RFC says things like pick a random number. And that's great because a large enough random number has a very low chance of collision. However, the way that some of the protocol fields in RFC 5326 are specified, the numbers are self-delimiting numeric values. They have variable sizes. Those variable sizes range from very small, so compact and efficient. But if you want to express a very large number, then you use more bits. So if you simply say pick a random number, and that random number can be anything in the entire supportable range, you could end up, quite often picking random numbers that that are quite large. You use a fair number of bytes. So, for instance, in the CCSDS profile for LTP, it says pick a random number. Yeah, but pick one in this relatively small range. We're willing to deal with the increased chance of collision there in order to get a higher bit efficiency out of the protocol as a whole. So I mentioned several times working with the IETF D10 working group. This slide just sort of compares what's going on right now in the two groups. In the top ones, the places where CCSDS is profiling or adapting some of the primary RFCs out of the D10 working group. So bundle protocol version 7, bundle protocol security. CCSDS is going to need to develop some security contexts of its own. Those will sort of be modeled after things that are in 9173. And those security contexts are going to be the things that agencies use to set up their security policies, right? Things like, there are requirements, at least in the United States, for encryption of, personal data for astronauts and things like that. So those security contexts will carry those, probably as well as requirements on nodes to verify sources of commands, and maybe even internal to the infrastructure, being able to authenticate that commands are actually coming from valid sources before you do something like send them across a deep space link, which is a very expensive operation if you're being DOSed across that. Network management is being worked in the IETF, and CCSDS is following that and trying to make sure that their network management concerns are supportable by the protocol that are being developed in the IETF. Some examples of things that the various CCSDS agencies are concerned about, very much concerned with like accounting on a much more granular scale than the IETF. So for instance, they want to be able to track if you send a command to a spacecraft from a mission operations center. They really would like to know, did that command reach the ground station? Was that command radiated from the ground station? And get timing for all of that information. So looking at least being able to support that in what the IETF is doing, maybe that might not be a level of accounting that most things on the ground, terrestrial networks that might be using bundle protocol would want to use, but it certainly is something that the various space agencies are interested in. And then sort of down below network management, these other things where there's a little bit of divergence. Again, a lot of the people who are working in these working groups are at least cognizant of what's going on in the other, and or actually actively working both groups. So we've got a good level of coordination, I think, going on there between us and the IETF. So in the area of bundle protocol and CCSDS, just talked about the profile of BPv7. Other things that are going on, looking at bundle and bundle encapsulation, so tunneling. of a bundle inside another bundle. It turns out that there are some issues we think that we found with the BPSec specification. So tunneling may be a good way for us to sort of operationally get around some of those issues while we try to sort them out. Quality of service is very important. As you can imagine, you might have science data and telemetry data coming back from a spacecraft, and if the spacecraft sees life on Mars, you really want that message to be prioritized highly and over regular spacecraft telemetry of this is the temperature of the battery, blah blah blah. So CCSDS is looking at ways to use extension blocks to provide quality of service extensions, and then define how those extensions are processed and how the different qualities of service are processed as bundles move through the network. There's some work going on also in compressed bundle status reporting and custody signaling. In the base bundle protocol, there are ways to request and formats for sending these status reports. If you request status reports, then you probably end up getting a lot of them. They're mainly there as they were mainly included in the protocol as a diagnostic tool. We see utility for using those kinds of things maybe to support some of these accounting mechanisms that I talked about. So the compressed bundle status reporting and custody signaling is looking at mechanisms to bit efficiently encode reporting, to be able to request reporting, maybe not from every node along a path, but maybe only some of the nodes, and then looking looking to see if we can leverage those bit efficient encodings to provide a reliability mechanism, something like the original BPv6 custody transfer at the bundle layer. Also, we think very important, especially since you may have multiple entities on the ground that are all interested in the data coming back from a spacecraft, looking at multi-point delivery, which you can think of as like bundle multicast. So one important way to achieve reliability in a network of bundle protocol nodes is to use reliable convergence layer adapters. So to make sure that the communications from bundle node to bundle node are in fact reliable. So you can do that easily with something like TCP, but TCP doesn't work particularly well over some of the mission scenarios, especially deep space links, where you might have very, very long round trip times, things on the order of minutes. And CCSDS had developed a reliability protocol that operates down at the link layer that could be used by these convergence layer adapters in order to provide that reliability in environments where something like TCP or QUIC doesn't work well. And so that turned into RFC 5326, or the link ladder transmission protocol. The issue with LTP that I talked about before was these self-delimiting numeric values, which are variable length encodings of integers. That lets you be very efficient if most of your integers are small, but you still want to handle a couple of big things. But it causes all of your headers then to be at least potentially variable length. And that can be a problem if you want to then process all of that through at very high speeds through something like an FPGA. So CCSDS is looking at a sort of a second generation LTP, which is this high performance reliability protocol that simplifies the segment structure somewhat so that you have more fixed length fields. It also goes through and removes some complexity that we haven't seen any of the agencies actually implementing in the LTP spec. Things like these mixed color blocks. LTP had a way of sending a block of data that had both reliable and unreliable information in it. It turns out that makes the state machine a little bit more complicated, and nobody was really using that. So we're looking at essentially splitting that out in the HPRP so that you can have reliable or unreliable blocks, but you don't get to mix the reliability with unreliability into a single block. And sort of just as an overview of the picture on the right, the way that LTP implements reliability that's sort of different from something like TCP. TCP, you generally want to acknowledge every packet, every other packet. With LTP, you're essentially sending all of the data and then acknowledging and then sending a message at the end of that says, okay, I've sent everything. Tell me what you got. And the receiver can then respond and say, either I got everything, we're good, or these are the bits that I need. Send just those again, and then you can proceed like that in rounds until you get the entire block across. And one thing that does is it can drastically reduce the load on the return or acknowledgement channel, right? If you're running TCP, you've got to take one acknowledgement every couple of TCP packets. If you're running LTP, that can be like one acknowledgement per transfer, so it could be one acknowledgement for a meg or 2 meg of data. And then finally, just some of the other stuff that CCSDS is working on. There's a solar system internet architecture document that talks about how the DTN architecture and bundle protocol can be used to cross support between agencies, like I talked about before. Scott Burley has a whole talk on that, and I encourage you to go have a look at that. It delves into the aspects of what does it mean for one agency to support another agency's mission? How would you do that? And how can you use bundle protocol and this solar system internet in order to make that happen? There's some other stuff in the application layer, this file delivery protocol that CCSDS has. They're adapting CFDP to run over bundle protocol as a networking layer. There's an asynchronous message service, AMS, that CCSDS has developed that they use for asynchronous messaging with spacecraft. And then this notion of schedule-aware bundle routing, which is one of the things that's probably more unique to the space domain, where in general we think that we're going to be, at least for the near future, for a lot of things, we think that we're going to be able to predict what the connectivity looks like, or there are certainly chunks of the network in which that kind of prediction is possible. So you've got spacecraft that are occluded by planets. When that's going to happen. That you're not going to have connectivity during that time, and when you expect them to come out of occlusion, and when you think that you're going to point an antenna at them and talk to them again. So with that, CCS developed a specification for this schedule-aware bundle routing, which, given a contact plan, a plan of who's going to be able to talk to who when, what the data rates are, prescribes what routes bundles that are injected into that network should take. The motivation there really was to ensure that different agencies don't end up with using sort of different metrics for routing that then just cause routing loops that cause bundles to not be able to make it to their destinations. In security, CCSDS is looking at this distributed and delay-tolerant key management architecture, a way for nodes to exchange public-private key information and update it and make all of that work in a delay-tolerant networking environment. And then finally, this notion, we've long had a notion of sort of the DTN and bundle protocol contribution to cross support and emergency services of sort of an application layer gateway that can be commanded to provide sort of local support to a spacecraft that's in danger or in trouble, right? So if you have a spacecraft that is somehow unable to communicate with Earth, unable to communicate with the things that it needs to, at the lowest layer, down at the data link layer, a lot of the spacecraft have mechanisms where emergency commands can be injected directly into some of the link framing. And you might want to be able to get to a spacecraft that is near the spacecraft that's in distress, and then cause the nearby working spacecraft to generate the appropriate link layer frames and emit those toward the spacecraft in distress. We've long had a thought of doing that. It's really an application, so probably in CCSDS that needs to be worked maybe even buy another working group, but we're certainly interested in helping out there and seeing if that can be something that's useful. So as you can see, by the time you put all this together, it gets pretty complicated. You've got the various protocols for communicating with spacecraft. You've got all of this cross-support work that's going on for how agencies can talk to each other. Luckily, CCSDS has a couple of documents that together sort of explain that at a high level, so that if you're just starting out and are interested in how all of this fits together, those are probably the places to start. There's a space communications cross-support architecture document that talks particularly about that cross-support aspects. It is a green book, so in CCSDS parlance, that's an informational book. There's also this cross-support architecture requirements document that gets more into requirements. It's a best practices book, something sort of between an informational book and a recommended specification. And then there's the solar system internetwork architecture document that I talked about before over on the right. And below those, sort of some of the pictures taken out of those that explain how the various protocols that CCSDS is developing are intended to be used together in order to effect that cross support and actually build a network out of all of these parts. So where's all this going? The current CCSDS bundle protocol specification that's based on bundle protocol version 6 is being used now on a couple of missions. It's being used on this PACE mission. It's also being used to support experiments on board the International Space Station. And the profile for bundle protocol version 7 is going to be used by LunaNet, the NASA LunaNet, and the ESA Moonlight missions. There's a little excerpt from the International Communications System Interoperability Specification, the ICSYS, draft of the ICSYS document up there on the right. And again, that getting a stable specification out is really a driver in order to support LunaNet and ESA, who are sort of chomping at the bit in order to get that so that they can turn around and hand that to their contractors in order to put folks on contract. Sort of the hierarchy of where the standards fit into the world, the standards in interoperability specify what can you do, right? What is it going to be? What are we going to ensure that it's possible for one agency to do with another agency? So things like networking, communication, security management, emergency operations. There's a level above that of coordination and policy that says, okay, within the set of things that you can do, what are you allowed to do? So just because maybe I can exchange bundles with a particular node, there may be some reason that I'm not allowed to. And then the governance idea is sort of above coordination and policy. How do you cooperate? How do you work together in order to make sure that the interests of all of the stakeholders are met? How do you resolve conflicts between those? A lot of the work that's going on in some of the LunaNet stuff, and the governance there is really concerned about, how are you going to resolve conflicts on, say, the moon, where you're not allowed to own property there according to the international space treaties. So how do you manage all of that? That's all interesting work that's going on, and some of it in IPNSIG is looking to help out in that area by providing a forum for various other organizations to come together and talk about what that governance is. Thank you very much. I hope you've enjoyed this, and I hope that you enjoy the rest of the talks at IPNSIG Space Summit. Good day.